I'm Tessa. I'm a new postdoc here. I was just graduated from UC Berkeley. And I'm going to tell you about this work that's now in PRB and it's on the archive too. And the main question is this hunk of ruthenium trichloride really fractionalizing? And so I first want to acknowledge that I did this work with my PhD advisor, Joel Moore at UC Berkeley. And we also had great conversations with James Analidis and Vikram Nagarajan and James's group, and Shubayu Chatterjee and Tomohiro Soejima at Berkeley. I don't know if I have to actually do much introduction on the Kitaev model, like people have been introducing it, but you have these bond-dependent icing interactions on a honeycomb lattice. So there are 3 inequivalent bonds. They each have their own distinct directional label. And we can write the Hamiltonian like this, where we have a sum of the nearest neighbors indicated by a bond direction, and then the icing interaction. This is a special model because of these plaquette operators that commute with the Hamiltonian. So each plaquette or each unit cell, I get one of these operators. So it basically reduces the Hilbert space tremendously. And there's an exact solution, which I want to just walk through because this is where we get fractionalization. So we have spins at every site of this plaquette. I transform the spins into Majoranas, which you can do generically. It's nothing, this is an exact transformation. With the caveat that I get this gauge constraint or this occupancy constraint, and that breaks apart each spin into 4 Majoranas. So each of the icing terms becomes just a 4 Majorana product term, and the special thing is that these B Majoranas, which kind of encode the directional information of the spin, commute with the Hamiltonian. So I just have these commuting operators on these bonds between these sites. And the ground state sector is when all of those are uniform. And this corresponds to all the plaquette operators being uniform as well. And so at the end of the day, I'm left with a free Majorana Hamiltonian, which you can solve through diagonalization. It was first introduced without materialization, but we've kind of talked about this at this conference already. The Jekeli and Kalulin figured out a way that you basically, due to spin-orbit coupling and Mott-Insulator physics, you can get these J1.5 moments that, due to the spin-orbit coupling, are not distributed spatially uniformly, and this, with the correct geometry, can kind of introduce these direction-dependent icing terms. What was mentioned earlier in this today, in fact, was that there's actually new proposals for cobalt-based compounds. So it's not just Jekeli and Kalulin's original one, but there's plenty of materials at this point that might realize this Kitaev model. And to focus really quick on ruthenium trichloride, we have these thermal Hall measurements, which are both challenging experimentally and challenging theoretically. But there's this beautiful data from the Matsuda group. The problem is that other groups have not been able to reproduce it so beautifully. Takagi talked about their data, which you can kind of see features of this plateau emerging, but then the Ong group was not able to get a plateau at all. There may be reasons to suspect that this might be resolvable, but currently I think there are some experimental challenges that need to be overcome. But instead, let's focus on inelastic neutron scattering, which has also been talked a lot at this conference. But the advantage is that it's probing just the spin degrees of freedom, so I don't need to worry about phonons so much. And these original data that are 6, 7 years old at this point, there are these broad features in the inelastic neutron scattering, which hopefully maybe we can interpret as being due to some quantum spin liquid. And we're comparing them with results from the exact Kitaev model. And then when you look at spin wave theory, the spin wave theory kind of doesn't account for these broad features. That was kind of the story from the original data. This paper's story was, I can fit the spin wave spectra and I see that there's a large Kitaev term, so maybe it's close to the Kitaev phase. And then, ruthenium trichloride does order at low temperatures, but if I put this in plane field, I can destroy the order. So once I've destroyed this order at 8 Tesla, you still have this broad feature at the gamma point. Sorry, this is the gamma point and this is the M point. And in the M point, there isn't much feature at all. So can we understand this? And I mean understand this as if we start from the Kitaev phase and we add perturbations to it, can we understand how this feature emerged and where the feature, like what would I expect to see at the M and gamma point for this Kitaev phase with perturbations? This is kind of analogous to saying, well, if I think I have an ordered phase of spins, I can do spin wave theory. So if I have a Kitaev phase, I want an approach that lets me compute these. Generally, this is a very hard question because you just have to solve a 2D quantum spin Hamiltonian. And for ruthenium trichloride, the most important terms are perhaps just a nearest neighbor Heisenberg term and this off-diagonal gamma term. And so solving this generically for all parameter range is a very hard problem. We have standard approaches, I would say, that we can use, which are like exact diagonalization or DMRG or variational Monte Carlo or spin wave theory. And these all have their usual caveats. So ED is limited to small size. DMRG you can only get to finite time or limited bond dimension. Variational Monte Carlo is kind of biased based on what states you put in. And spin wave theory only works for ordered states. There's also some analytic work where we're looking at, can we describe the low energy, these Majorana degrees of freedom with an effective field theory? But that's only going to apply in the low energy limit. So if we want to understand all the features of neutron scattering, it's not going to be satisfactory. And then there are a lot of mean field theory based approaches, and most of them focused on static quantities. But there was this work by Knoll, Bhattacharjee, and Musner, which I'm going to call the KBM paper, where they introduced an augmented mean field theory to capture dynamic quantities. And what I'm going to talk about is an alternative, this time-dependent mean field theory approach, which I will show you can capture all the dynamic quantities of the exact result, and I think improves a bit upon this KBM approach. So first, let me just review what's going on with Majorana mean field theory. So let's imagine now I have the Kitaev term, but I add a perturbation. So I have these spins. I can still do this Majorana decoupling. Where this, as I mentioned, that result is not limited. It's just some kind of transformation I can always do. I then want to do a mean field decomposition of this 4 Majorana term. So I just break it into bilinears and with the expectations in the very usual form for mean field theory. Now, importantly, I'm always computing these expectations. I have some state in mind for what I'm computing these expectations with respect to. So I have some Hamiltonian that's acting on a state. I then decompose each of these 4 Majorana terms with respect to that state. So I compute these expectations with respect to that state, and that breaks my Hamiltonian into 3 pieces: a constant piece due to that term, a B piece due to this term, and a C piece due to that term. And so I can write that this mean field decoupled Hamiltonian, I'm saying like H subscripted the state that I'm acting on. So that's important. And then when you're looking for the ground state, you just look for a self-consistent state that's the lowest energy where you compute this. You can then do in the mean field form, diagonalize this Hamiltonian, it's quadratic, and then compute the expectation values, and you look for a fixed point of that. You find a fixed point, and in these C Hamiltonians, I'm going to call their excitations gamma, and the B Hamiltonian, I'm going to call them chi. The chi is reminiscent of the bond fermion picture. And in the ground state, all of these operators annihilate the vacuum. And so the energy is just given by this expression. Okay, so that's the static property. So why, in the literature, you can find claims that mean field theory fails for the Kitaev Hamiltonian. So what do we mean by that? We can reproduce the ground state energy and the itinerant Majorana, the C Majorana band structure. So that's essentially saying this HC mean field decoupled state is equivalent to the HC, the one that I get from just setting all the conserved quantities equal to 1 or minus 1. However, if I think about adding flux excitations to this Hamiltonian, these are the chi operators. These chi operators have a higher energy than expected from the exact solution of 4 delta F instead of delta F, where delta F is the flux gap. Additionally, if we compute time evolution with the mean field decoupled ground state, the Hamiltonian decoupled with the ground state from mean field theory, we encounter a problem. So this is the main dynamic quantity I'm interested in, which is the dynamic spin-spin correlator. If I rewrite it in terms of the Majorana, the e to the IH on the left acts on the ground state, so I just pull a ground state energy out. But the inside one, I just get a time evolution operator. Now, in mean field theory, the advantage is that due to the structure of the decomposition, the C's and B's degree of freedom split from each other. So I can just think of it as a tensor product. So in this big operator, I can pull all the C degrees of freedom to the left, all the B's to the right, and then the B's collect and actually cancel out the constant phase. So it's just a phase. This is in the exact solution for the moment, in the exact Kitaev point, so no perturbations. And what you're left with is just the C Meyeron is sandwiched with their mean field Hamiltonian. So they're just evolving under the mean field ground state Hamiltonian. And this is not what you get in the exact solution. In the exact solution, the thinking is acting this Bj on this state, you excite one of these operators. So you now have flipped the sign. And then these C Meyerons are really moving with respect to the Hamiltonian, this Hamiltonian, not the free Hamiltonian. So in this approach, you're somehow missing the fact that there's, the C's are really evolving with respect to this flipped state. So mean field theory fails. And this is what KBM used to introduce their augmented mean field theory. So what they did was they took the mean field decoupling and they added an operator sigma that scales the C part of the Hamiltonian. And the idea is that this operator anti-commutes with the B's. And it's an operator that also has plus or minus 1 as its eigenvalues. So if I do this same computation for the SI of T Sj, when I'm pulling the B past the C Hamiltonian, so now the B does not commute with the C Hamiltonian, it's going to reproduce this flip. And that's like the main point of why they added this modification. The problem is you need some additional approximations. So the C and B Hamiltonians in these mean field decoupled, the mean field decoupled C and B Hamiltonians no longer commute with each other. So you need to use Baker-Campbell-Hausdorff to break apart the exponential in the previous slide. So you can maybe ignore the commutator parts of that for small perturbations. But that's an approximation. Additionally, in the exact result, when I create this, I act on this B operator, I flip one of the signs of the conserved quantity, that will persist for all time. But with perturbations, these excitations start to move around. So at some point, once the excitation has moved far enough, you might say, oh, well, I should be evolving with just the ground state Hamiltonian. So they add time dependence to this flip term that they say will go to 0 once this flux, which they're probing with this part of the expression, becomes small enough. And they also have to adjust S of Q omega self-consistently to get the correct low energy or low omega behavior. So there are a couple things that I think could be improved on this. One is that it's a non-symmetric implementation, so the C's and B's are no longer symmetric. So what happens when I add a magnetic field? It's not exactly clear how to extend the method to that. And then you had these several approximations that you had to do, several additional approximations, including the approximation of using mean field theory, including some things that we kind of had to put in by hand to correct everything. So now I want to go back and reevaluate what we said. When we said that we failed, mean field theory failed, we were making some implicit assumptions. The first is that the energy of this state was said to be for delta F and not delta F, but is it even an eigenstate? And it is an eigenstate of this mean field decoupled Hamiltonian, but that's the wrong question. If I think about the full Hamiltonian acting on this state, I would then mean field decouple the Hamiltonian with respect to that state, the state that I'm acting on, and it's actually not an eigenstate. So this 4 delta F energy is not actually corresponding to the energy of any eigenstate. And then I said the other problem was that I was doing time evolution with respect to the mean field generated by the mean field decoupled Hamiltonian. But the alternative is that we can do infinitesimal time evolution. So I'm still saying the time evolution operator is generated by the full Hamiltonian, which then I act on the state that I'm acting on some state. I decouple with respect to that state, and then I can do a small evolution in time. And that's the essence of time-dependent mean field theory. So this was kind of pointed out by Nasu and Motome. This idea has been around for a really long time. This is not a new idea. Dirac pointed this out in the 60s. So in the Nasu and Motome's work, they first find a self-consistent Majorana ground state with respect to some Hamiltonian. They're then thinking about quantum quenches, so they want to evolve under some different Hamiltonian H prime. And so they want to do some small evolution. And when I've done this mean field decoupling, I'm always left with a quadratic Hamiltonian. So if I want to involve some Majorana state with respect to that Hamiltonian, it's sufficient to just evolve the annihilation operators, the operators that annihilate that state, with respect to this new Hamiltonian. And due to the quadratic nature, this is just multiplying it by some exponential of some matrix. So the procedure is then I Meanfield decouple H prime with respect to the state that I'm acting on, and then I use that Meanfield decoupled H prime to evolve the state a little bit in time, and I do this until I'm at the time that I care about. At the end of the day, this is just linear algebra. I'm manipulating 4n by 4n matrices with a system of 4n Majoranas, so n sites. So this scales much better than exact diagonalization, which goes as 2 to the n. So we wanted to apply this to correlators. There's a bit of complication, but it's all just how do you actually do these computations. So we start with the same thing. We have e to the IH on the left that's acting on the ground state, so that just becomes a phase. But the inside is the full, this is a full Hamiltonian. And I'm then going to peel off the right side of this into this wave function, psi of t. And so if I'm able to compute this correlator, we can in sense use time-dependent mean field theory to evaluate this quantity. So we've given approximate expression from psi of t from this time-dependent mean field theory, and we say how to evaluate this correlator. So here's the high-level flow of what we do. We think of some Hamiltonian, which is the Kitaev Hamiltonian plus some perturbation. We find the self-consistent ground state V. We then psi of t equals 0 is just given by the operator acting on V. Then you mean field decouple the Hamiltonian with respect to that state. We can then do a small amount of time evolution to get psi of t plus delta t, and then we can compute the correlator at time t. And then we just go back and forth until we're satisfied. And then we can Fourier transform that to get S of q omega, which allows us to compute inelastic neutron scattering spectra. Before I show any results, what are the selling points for TDMFT? The first is that it reproduces the exact result. So nowhere in this did I have to talk about these fluxes or C Majoranas. I mean, I talk about them implicitly but I didn't have to appeal to the exact result to reproduce it. We can get to fairly large systems, so 70 by 70 unit cells. It can treat arbitrary perturbations. So if it's a perturbation we haven't thought about, you can just plug it into this machinery. You don't need to do any additional thinking. And it's a self-consistent in the sense of if we apply mean field theory self-consistently like this, we don't have any of these failures that I talked about earlier. The only approximation I'm making is that at every time step, mean field decoupling the Hamiltonian makes sense. And I'll talk more about that later. But we also compared with some DMRG data and got fairly good comparisons. So this is from this Golka et al. Paper where they did infinite DMRG for the Kitaev Hamiltonian in the presence of a magnetic field. And with no magnetic field, we should perfectly agree, but at low omega, we disagree some. This is probably due to the finite bond dimension in the DMRG. And as we introduce magnetic field, we kind of see that the change in the spectrum where I'm adding this kind of oscillatory features at low omega, we're capturing that in our calculation as well, and it kind of continues to be captured. At some point, you expect this to break down because it's like a perturbative method. Okay, so I don't have to just think about the magnetic field, but we can certainly do it in a magnetic field. So what are the roles of these Heisenberg and gamma terms that I've talked about earlier? For just a Heisenberg term, it kind of just shifts the features around. This is due to the fact that the Heisenberg has a diagonal coupling that kind of rescales the Kitaev in some sense. So it's just kind of shifting the features around. The gamma term seems to add spectral weight around this kink in the exact result and doesn't do much at the higher energy features. Kind of adding both of them at the same time, it does both of the effects, gets a little bit messier. And then for a magnetic field, we again see these oscillatory features at low omega, as well as losing a little bit of power towards these kinks or these, sharper features. And we can also compute the inelastic neutron scattering spectra, as I mentioned earlier. And in particular, we can look at the M point. And we're not seeing any evidence that the M point signal that's in the exact Kitaev phase is disappearing substantially due to the presence of these perturbations. So I'm not sure how to explain the data on ruthenium trichloride, but if somebody can explain that to me, that would be cool. Now, I want to say there are a couple caveats here. One is that we've kind of completely ignored this gauge constraint. The way it's taken into account in the exact result is that these di actually end up creating all these fluxes, and it turns out to have essentially no effect. But in the Meanfield treatment, we're doing something that's consistent with what other people do in the literature, which is basically the Meanfield theory kind of applies this constraint on average, which I think is a very standard approach for adding constraints, but I think we should think about that more. The second, there's this question of the basis. So if I computed S of Q omega directly, I would replace the local operators Si and Sj with S of Q. And then when I think about Meanfield decoupling with respect to S of Q acting on the ground state, it's not going to change any of the expectation values, in essence, because you've distributed that flux across every site of the system, which will average to 0 in the thermodynamic limit, 0 change. But I think it makes more sense to be computing in real space, since that's where the mean fields are computed. And then you might have seen this, there's small unphysical response in the S of Q omega that I was plotting. For some of the parameters, there's negative values, which should not happen strictly. And there are small violations of the sum rules at the level of percent, so like 4 or 5% for the largest parameters that we thought about. Okay, so then the second caveat is, when do you need to use TDMFT? People have been doing mean field theory for a long time. When the normal story for when mean field theory is valid is that the coordination number goes to infinity, so how many nearest neighbors I have. And I think this will still lead to TDMFT not being necessary. The idea is, if I'm applying some local operator to my state and I recompute the expectation values, then the local operator will only change finitely many of them, but the infinite other nearest neighbors will kind of wash that out. So there's some correction, but it probably doesn't matter. But in the Kitaev case, we're in the z equals 3 case, so it isn't true because z is infinity. Instead, there's a different reason for why mean field theory is valid. So at the high level, I'm replacing this 4 Majorana operator by these 2 Majorana operators with expectations. So let me just call the difference between these delta, because I'm always thinking about quadratic states, like the ground state of a quadratic Majorana Hamiltonian. By Wick's theorem, delta is equal to 0. But I can look at the fluctuations of like delta squared, and it factors in this way. 1 is exactly just the operator squared its expectation. So it's basically saying, in order for the fluctuations to be small, I need the fluctuations in one of these 2 operators to be small. So one of these 2 operators needs to be approximately conserved. And by that I mean it needs to be approximately its expectation value, and any constant commutes with the Hamiltonian, so it's approximately a conserved quantity. This is exactly what happens in the Kitaev case, where the B's kind of split off and are conserved. Then TDMFT becomes necessary if your calculation changes the values, moves you between sectors of this conserved quantity. Okay, I think it's a fair question. Does this only apply to the Kitaev model? And the answer is no. I can write down, this should work whenever mean field theory is valid in the second point sense of the last slide. And so I have this kind of toy model for how a different model where you need to use it. So I'm just thinking of some conduction band of electrons and some Ising spins, but they're still spin halves. And they couple via Kondo term, but again, only the z component of the Ising spin. So the only component of the spin that I think about is the z component. So I can just say, okay, the ground state, as I make J ferromagnet, is just going to be they're all aligned with each other, and this changes the conduction band. But if I choose the right sign of K, it's going to give me an easy way to describe the ground state. But if I look at these correlators in the x component of the spin, because the x flips one of the values of the S of z, I'm flipping one of these conserved quantities, and therefore I'm evolving under a different Hamiltonian than just the Hamiltonian of the C's. This is an exact calculation. And if you do mean field theory, it's going to fail in the same way as the Kitaev model, so it's not really failing, but if you apply TDMFT self-consistently, you'll reproduce the exact result. And so it kind of, just emphasizing that this is not unique to the Kitaev model, it applies to other models too. Okay, so my main conclusions are we have the Kitaev model, which we're interested in studying. We have all these material candidates that we want to look at, but the comparison with the experiment can be quite difficult. But with this model, we can take any small perturbations to the Kitaev Hamiltonian. If you think you're still in the Kitaev phase, then perhaps this the mean field theory will remain valid, and then you can compute the inelastic neutron scattering data, for instance, or if there's a different quantity you can compute, we should be able to compute that as well. And then it's not just the Kitaev model, it's an approach that could be used whenever you're trying to apply mean field theory. And with that, I just put this flow chart for the calculation, and that's all I had.
Thank you. Very good talk. So, quick question. Can you introduce magnetization? I mean, you're in the spin liquid phase, but you want to see the instability. Mm-hmm. Can you introduce another channel in your approach and then also to find it?
Yeah, so I just did the one channel for simplicity, but when we put a magnetic field, we do all the channels. So, yeah.
Thank you.
So I have not a well-defined question, but so I know some years ago people looked on connection between Majorana fermions that Kitaev did and usual Abrikosov fermion parameterization, and there were some papers, but again I didn't follow to current times, where people making kind of mean field type of considerations based on Abrikosov representation. Yeah. So can you comment on similarities or difficulties, or if I take perturbed Kitaev model, use Abrikosov, and then more or less standard decompositions that I can do mean field, how it would differ or not from?
Yeah, I remember, so in one of these papers, I think they were mostly focused, so the Majorana representation is equivalent to the Abrikosov representation. You just need to do a transformation. So you can think about all the channels in the Abrikosov fermions. There is some difficulty, like the most naive thing doesn't reproduce the energy. They're off by a factor of 4 or something. I can't remember all the details. But I don't think they were really, in the papers I remember, they weren't looking at like the dynamics. And so I don't know what happens if you say, instead of Majoranas, I consider Abrikosov. And so this is where I think like mean field or the exact solution does enter into the calculation. I know that this approach reproduces the exact result. So in principle, if you can write down an Abrikosov mean field theory that reproduces the exact result, that would be another way to think about perturbations. And I don't know if you're going to get the exact same thing or not. I would hope you'd get something quite similar.
You mentioned fluctuations, but you commented on when the mean field will be good when some quantity is 0. Yeah. But in principle, you can calculate fluctuations by doing the truncation in the next order in Zubarev by writing down the operator equation. It's hard, but it can be done. Have you tried that? I mean, because since the technique works in this leading order, it's worth going to the next order, right?
You mean computing these fluctuations?
Exactly. Write down the equations for these now. In the next order, you can truncate. Mean field is basically an infinite order coupled equation. You are truncating in this order, and then the next order will be fluctuations. It's worth doing since your technique is so successful.
Yeah, I don't know. I guess I'm unclear about how you would exactly incorporate the next order. Like, am I needing to think about some path integral?
Yeah, you'll get many more operators, and then you'll make the same truncation in that order. Okay, that's what it is, at this order 4. So but you haven't tried that.
Yeah, it would be great to talk about that.
Okay, and my other question is something that worries me a lot whenever I hear anything topological is disorder. Does your technique, can your technique include disorder? Suppose the Hamiltonian had some disorder. You can parameterize it.
Sure.
Can you still do the actual work? Probably you can, right?
So it depends on what kind of disorder. I think if you think about like having flux disorder where I have some of these bond fermions in your low energy state, you probably can take that into account. The idea is just that the way that we find the ground state is we start with the uniform flux, but I, in principle, do not need to actually distribute the flux uniformly. I can put some of the, like some bond fermions into my state and look for low energy states. So if one of those ends up being lower energy, you can still do this procedure.
Yes.
So that kind of disorder, I think we can accommodate for bond strength disorder. I think that can also be accommodated.
I think as long as you include any disorder, it's okay, because there's this myth that topological system is immune to disorder.
Yeah.
But that's only for infinitesimal disorder.
Yeah.
Any kind of disorder, if you can do it, it will tell you to what extent it's immune, and I think it's worth thinking about.
Okay.
It doesn't matter what the disorder is as long as you can handle it.
Sure. Yeah, I think we can handle disorder.
We should talk about this.
Okay, yeah, for sure.
So when you do time-dependent mean field theory for an ordinary magnet, then if I remember right, maybe you can correct me, then you just get, if you look for small fluctuation, you just get spin waves in RPA. So you get the standard spin waves out. And so there we have some real excitations, which are the fluctuations of the order parameter. So what about here? What are the small excitations of the fluctuating order parameter? What excitations are they in this system?
I mean, I think these excitations are the C's and the B's, unless I'm misunderstanding your question, right? Like,
yeah, so my feeling is that we have one more excitation. So if you start with fermions, then interacting fermions, and then when the time-dependent mean field, and then we have a theory of magnons coupled to fermions. Yeah? And so in analogy, I would have thought that something similar may happen here, that I get a theory of Majoranas and D also feels coupled to some extra degree of freedom.
But I guess I only have the 4 Majoranas per site, right? Like all the degree.
You already have 4 Majoranas per site. So there's obviously a double counting issue here in these gauge theories. Okay.
Okay, maybe we can talk later. I don't know.
Thank you for the talk. It's very, very clear talk. I was wondering, you showed there is this unphysical response.
Yeah.
Do you have some insight where it comes from, and perhaps would there be a way or a scenario to cure it?
Yeah, we've thought about how to fix it, and I think there isn't really a clear way. If we can, the issue comes from the fact that I'm not doing the time evolution operator exactly, that I'm by the mechanism of our approximation, doing it approximately. So if I could do that more accurately by computing fluctuations, then perhaps it will decrease the size of the error. The other alternative is that you could use like the exact Lehmann representation result, and maybe you can think about, I just want to look for self-consistent mean field states and try to account for all of those, but there are other challenges in that, like you might be it'd be hard to get the counting right in the presence of perturbations. So it's not actually clear exactly how you'd remedy this. But the issue is very small percentage of the support is negative. So usually, again, like % level errors. And this isn't unique to ours. The KBM approach also has some negative support. So I think it's just a challenge of doing it approximately.
Questions? So I have a question. You mentioned about the violation of the sum rule by a few %.
Yeah.
Is that because of the resolution of the frequency, or there is more fundamental reasons for that?
Yeah, so we can kind of tune the resolution of the frequency and look for convergence. So it's not that, it's fundamental, and these violations go to 0 as I go to the exact solution, because the exact solution satisfies all these bounds. It's very similar to the previous question. It's the fact that we're making approximations, basically.
So this bound is not really a conserved quantity. in this away from the exact solution.
Yeah, I mean the issue with doing the time dependent, like at every step I have a slightly different Hamiltonian that I'm evolving with respect to. And I'm neglecting some feature of that, so it's destroying things that should be conserved if they don't commute with every single Hamiltonian. Yeah.
Yeah, thank you very much for the nice talk. Just a question to that. So if you would like to cure that, what would help more? To go to the next order, so that means include fluctuations, or to do a better approximation to what you're doing at every step? So which is, let's say, the contribution that you think will cure these issues much better? Because I guess that you did an approximation because you didn't know how to, otherwise you cannot evolve. But can you cure that by going into the next order? So by including the fluctuation effects?
Yeah, I mean, if there are ways to account for the fluctuations, then yeah, it should cure it. It should get better. Because yeah, the point is that we're just neglecting things by neglecting the fluctuations of delta. Right. But if I can account for those, it should get better. Yeah. But I just don't know how to do this. So.
Okay. So okay, maybe we can talk.
Sure.
Okay, more questions? If not, let's thank Tessa for the beautiful talk.